Hi everyone, my name is Ella Cho, and today I'll be presenting my poster on the Cerebellar Satiation Network as a forward model for feeding. So in this project, my colleagues and I were interested in creating a model to describe the process of adaptive feeding, which essentially is a process that prevents us from undereating or overeating, but still being able to obtain sufficient nutrients from food. Um, Based on two main premises, we believe that this is all mediated by the DCN or the deep cerebellar nuclei in the cerebellum. And those two premises are one, the cerebellum is known to be very involved in adaptation, especially when it comes to motor control. And the second is that one of my mentors, Aloysius Lowe, discovered a couple years ago that when we selectively activate the DCN, we're able to induce satiety in mice. So in synthesizing these two main findings, we speculate that the cerebellum is able to mediate adaptive feeding through this forward model. So a bit about the model, we think that there are three main inputs into the DCN or cerebellum. The first is sensory info, which could be the sight or smell of food, for example. The second is internal state, which would be anything that's not sensory info that can be internally sensed. So, for example, that could be intergastric nutrients or one's like current hunger level, for example. And the last input would be priors, which we define to be any prior experience that one has with food. So we think that all of these things feed into the cerebellum and helps it make a prediction on how much food to eat in a meal to achieve a certain level of satiety. So after the eating is performed, there's an outcome level of satiety after the meal. And that can either be equal to the prediction or unequal to the prediction. Um, but when there is an imbalance between prediction and outcome, that ultimately becomes a prior and gets refed back into the cerebellum. And that allows the cerebellum to make a more accurate prediction in upcoming meals. So, in summary, we believe that this imbalance between prediction and outcome ultimately drives adaptation over time, and that is mediated by the DCN in the cerebellum. So, in this project, we kind of dissected our model and observed the relationships between each of those inputs and the DCN. And to perform many of these experiments, we use a technique called fibrophotometry, which uses fluorescence in the brain as a proxy for neural activity. So we're able to generate fluorescence in the brain using a genetic virus called GCAMP. So when we surgically inject the virus, neurons with the GCAMP will fluoresce whenever there's heightened activity of calcium. And so that fluorescence becomes a proxy for neural activity because of the calcium. And we end up getting these traces that look like these green spikes. You can think of the y-axis as representing neural activity and the x-axis as representing time. And you'll see throughout the poster, I usually have a red line that represents the time point at which I introduced a stimulus. Um, so from these experiments, a lot of analyses that we do are comparing like pre-stim and post-stim neural activity, or even just comparing activity in general um, over different conditions. So normally when we inject GCAMP into the DCN, we observe neural activity when we food drop or just place food in the cage of the mice and they eat it. So we're interested in dissecting this behavior and seeing which part of feeding is the DCN actually involved with. So um, the first way that we probed this was seeing whether the DCN could be activated by food cues or sensory information related to food, so like the sight or smell of food. So in this experiment, we recorded DCN activity when we presented peanut butter for the very first time to mice. Um, and they weren't allowed to eat it. We just recorded activity right when we presented it. And then, as you can see, there was very little neural activity mainly because the mice did not process that this peanut butter had nutritive value. However, after we let them eat it for a couple of days, when we presented it, they then showed heightened neural activity. So this tells us two things. One is that, yes, the DCN can be activated by sensory information. And the second is that there is some learning component to this, as it was only after they gained experience with the peanut butter that they were able to exhibit a response. So for the sake of time, I won't go through this prior experiment, but to test this learning capability of the DCN, we essentially performed a similar experiment but using Jello. And we did this with calorie Jello and then very similar looking calorie-free Jello and measured the neural activity response. So you can go ahead and read that as a follow-up for this learning capability of the DCN. So in addition to sensory info, we wanted to see whether, apart from that, could the DCN be activated by pure intragastric nutrients. So to do this and to bypass all the sensory modalities involved with eating, we use a technique called gavage, where we directly infuse liquid into the gut of these mice. And to test like a nutrient and non-nutrient condition, we infuse water and then ensure which has calories in it. Um, so when we observed the mean neural activity in the DCN in response to these infusions, we found that ensure elicited a higher mean response than water, which suggests that the DCN can be activated by nutrients themselves and nutrients alone, in addition to sensory information alone. So by now, I hope I've convinced you that the DCN is quite involved with many aspects of feeding, um, and that sensory info, internal state, and also prior experience um, are each able to activate the DCN and are inputs to the DCN. So to probe our model, we designed an experiment in which we wanted to observe whether changing the balance between prediction and outcome could induce adaptation. And so to do this, we first surgically injected a dread into the DCN of these mice. For those unfamiliar with chemogenetics, a dread is basically a genetic virus where we're able to activate the region that we injected the dread by a chemical injection of CNO. Um, so as a reminder, when we activate the DCN, the mice feel fuller. Um, so in this experiment, we trained our mice to eat one meal a day for 3 hours. And at the very end of the meal, in half of the mice, we injected them with CNO, making them fuller than they expected themselves to be after eating just a regular meal of chow. So we found that over time, the mice with this post-meal activation dramatically decreased their meal sizes as a result of adapting to the increased fullness of their meals. So what this tells us is that, one, an imbalance between prediction and outcome is able to induce adaptation. And two, this is mediated by the cerebellum, as we only observe this adaptation in the DCN activated mice. So in summary, adaptive feeding is a process that ensures that we eat just the right amount in meals. And we think that this is driven by the cerebellum, as it's heavily involved in feeding, as we've shown in our various experiments, and we're able to induce adaptation by activating it at certain points of meal consumption. In terms of future directions, we plan on getting more temporal accuracy by using techniques such as optogenetics instead of chemogenetics. And we also plan on trying to rescue the phenotype that we observe in the final experiment I presented by possibly inhibiting the cerebellum instead of activating it. And yeah, that basically concludes um, the summary of my project. And if you have any questions, feel free to email me at ella.cho@sas.upenn.edu, which should also be linked in the Penn Presents platform. Thank you.